So for our last talk session of the week, so with Tristan Guyon from Montreal. So yeah, take it away.
So good morning, everyone. So I'm going to present today some joint work with Arnaud Guillain and Manon Michel, and it deals with non-reversible sampling. So we're back to MCMC, and I'm going to present to you how we go beyond translations in the Event-chain Monte Carlo setting. Yeah. So just to give a brief introduction, so the idea behind Event-chain Monte Carlo is that you build these non-reversible translations. So it was introduced in 2009 for hard spheres and in 2014 for more general potentials. And the idea is that you move one sphere on a translational motion, and when there is an event, the other spheres is moving, and then you get this created motion that you build via the non-reversibility. So by breaking the detailed balance, Event-chain Monte Carlo has allowed to investigate numerically the hard sphere fence transition in 2011. And now we are trying to see if we can replicate this type of results on different systems. And what we are interested in are anisotropic particles. So some work have been done in this direction. So for example, tethered hard disk dipoles, where so in this system, the particles consist in two spheres for which, in addition to the no overlap condition, they cannot be farther apart than a certain distance r. So this can be studied in the Event-chain Monte Carlo setting because you can just translate one disk at a time. So this was done in 2022. And what you can also look at, for example, are three-dimensional polyhedrons. And for these, the method that was used was to use ECMC to translate the particles. And in addition to that, at regular intervals, you add reversible rotations. So the idea here is to see whether we can build algorithms that are non-reversible also for rotations. And taking a step further back, how to build general deterministic flows into the Event-chain Monte Carlo setting. So I'm first going to do a brief reconstruction of the Event-chain Monte Carlo setting. And then I'll try to pinpoint what fails exactly when we go to anisotropic particles. Then I'll show you how we introduce general flows into this setting, and I'll finish with some numerical results. So we start from the reversible setting. So you want to sample from a set which is distributed according to the Boltzmann measure with the potential U. What you need to check is that you have the global balance. What is often done is to impose the more restrictive detailed balance condition, which is here. And this is at the core of the Metropolis algorithm, where you have a certain proposal probability, and then you know that your algorithm is correct if you accept with this acceptance probability. Now, the idea is to build on the Metropolis algorithm. So the system I want you to have in mind is a particle system with symmetrical pairwise interactions. And the picture for the Metropolis algorithm is that you get this diffusive behavior in the state space. To avoid that, we introduce lifting. And so in addition to our configuration, we introduce sphere index I in a direction E, and we add persistence in the motion in the sense that we're proposing sequentially the same move until there is a rejection upon which you have to change I and E. The problem is that for finite time steps, at some point, you're always forced to flip the velocity and go back. And this is something we want to avoid. And this is why we go to the continuous time limit. In this limit, you obtain a rejection rate, which has this form with the positive part of a term which involves the gradient of the potential. So this gives you that the rejections happen with a Poisson process with this rate. And because we're now in continuous time, we can use the translational symmetry of the pairwise potential, because it will translate to a symmetry between the moving sphere and the sphere that triggered the event. So instead of flipping the velocity, instead of just going back, what we can do is to instead go forward with the other particle in the same direction. So this is the straight kernel. And so in addition to that, for ergodicity purposes, you will typically need to draw new I and E at regular intervals. To introduce more general flows, we use the mathematical framework of piecewise deterministic Markov processes. So we still have our space distributed with a Boltzmann measure with potential U. And we introduce a lifting space V with a certain measure mu V. And the four main ingredients are the following. So we have a deterministic flow, which acts both on X and V. We have events, which happen with a Poisson rate lambda, and which trigger a kernel Q. So these events play the role of compensating for the flow in order to sample for the correct probability distribution. In the case where you're allowed to touch the boundary, for example, for hardcore problems, you need to define a boundary kernel. And also, so still for ergodicity purposes mostly, you define refreshments which happen with a certain Poisson rate, which trigger a refreshment kernel, which will typically be just a direct sampling of mu V. Now, PDMPs are studied through the infinitesimal generator. So on a function f, it yields the following form, where you have a transport term, an event term, and a refreshment term. And the way the boundary gets taken into account is that the functions that you're interested in must satisfy a boundary relation. So this is where the boundary is taken into account. To satisfy the global balance, you just need to check that the integral of the generator against the full probability measure gives 0. And now I just want to make a quick comment on the refreshment term. This refreshment term will always self-cancel. So in a sense, it will not contribute to the global balance, but it's there for ergodicity purposes. So ergodicity will often rely upon the refreshments. Now, so a precise link has been made between Event-chain Monte Carlo and the piecewise deterministic Markov process framework. And so the your variable V is so the pair IE, take the uniform probability. And for the flow, you just give velocity E to the sphere I. And nothing else happens in terms of the flow. So you have the straight kernel that I mentioned before. And with this framework, you can also go a little bit further and introduce the direct kernel, where in addition to moving on with the other sphere, you add stochasticity at the events by redrawing the velocity according to the correct event measure. So now I'm going to show you what can fail in terms of Event-chain Monte Carlo for anisotropic particles. So the system I'm interested in is the system of hardcore dimers. So one particle is composed of two hot spheres which are stuck together. So in terms of ECMC, the collisions will just reduce to sphere-sphere collisions. And this system is interesting because it cannot be thermalized by translations. We have to have some rotations of some sort. So a first algorithm that we can devise is by taking the algorithm that was made for polyhedrons, where we use Event-chain Monte Carlo for translations. And in addition to that, at each refreshment, we propose a stochastic number of metropolis rotations. This gives an algorithm which is non-reversible for the translational part, but reversible for the rotation part. So this will be a reference algorithm on dimers. If you try to go to reach non-reversible rotations, what happens is that, so let's imagine that you want to rotate the dimers around their center. So for the flow variables, you would take the index of the moving dimer and a plus or minus, depending on whether you're rotating clockwise or anti-clockwise. And with this collision, what you can see is that the first dimer hits the other particle. So since you're in a hardcore problem, it's the boundary of your problem. The first dimer hits the boundary with a faster rate than the second dimer is leaving it. And this creates an imbalance in terms of probability flows. And as a consequence, you lose the symmetry between the colliding spheres. And this prevents you from using the straight kernel. You cannot always move on with the other particle. You have to allow for some backtracking. So, which is something we want to avoid. The situation here is that this collision is only sensible to these two colliding spheres, but the flow itself depends on the dimer orientation. So we don't have a flow phi of v, we have a flow phi of xv. And the question is, what conditions must these general flows follow? So we want to first give a little bit more precision of what's going on with the translational schemes. So general translational schemes take this form. And when you write the global balance condition, so you write that the integral to the generator is 0, you integrate by parts and work things out a little. What you obtain is this equation. And then if you integrate it over V, the terms with the event rate lambda disappear. And what you get is a necessary symmetry for any translational flow, in the sense that all what goes into the event on the right-hand side must be balanced out exactly by what goes out of the event. So this is a necessary symmetry of our flow. With this relation, you can also, since the right-hand side is positive, you can deduce that there exists minimal event rates. And this minimal event rate happens to coincide with the metropolis rejection rates that arose from the infinite mole metropolis construction. So in a sense, this construction was optimal. And so with this rate, the equation above becomes this one, and this gives you the condition that the kernel had to satisfy. So basically, it needs to send this positive part into, to turn it into a negative part. So these are the conditions that you need to satisfy for the process. And in addition to that, so these are in the bulk of your set. On the boundary, you have the same conditions where you just need to replace the gradient of the potential by the normal vector on the boundary. Now, if you try to do the same reasoning for general flows, you also get a minimal event rate with a slightly different form. So it's taken as a positive part of the sum of three terms. So the first term accounts for the change of density in X space. The second term accounts for the change of density in V space. And the last term is a divergence term, which accounts for the volume change, for the flow. One thing that's interesting is that it's possible to suppress all events. We call these ideal flows. And to make lambda m go to 0, you have to take you have to be in a setting where the sum of these three terms is equal to 0. And this takes the form of a continuity equation, where it essentially tells you that the flow needs to conserve the full probability in x times v. So this is interesting because it would allow to suppress all events. However, this way of constructing the flow strongly depends on the potential u. And this is why we introduce uniform ideal flows, where we're going to suppress events only up to the physical parts, which was already present for translations. So you have to take that the sum of the last two terms is equal to 0, This also takes the form of a continuity equation, but what you conserve is not the full probability in x times v, it's probability in v and volume in x. So you conserve probability for the corresponding problem where you put u to 0, or if you want the corresponding output problem. Now this is interesting because this flow construction is independent of u. And moreover, with this, all the terms that were specific to the non-translational part of the flow cancel out. And so you can just build on all the machinery that was developed for translational flows. In particular, we know the necessary symmetries for the flow and what relations the kernel needs to satisfy. So I'm going to give some explicit flows. So for spheres, we build non-reversible rotations for spheres in the following way. So in addition to the index of the moving sphere, you have an angle, which will essentially tell you where you're at in the rotation. For the flow, it's a bit similar to translations in the way that you give to the sphere I a velocity going in a certain direction, but this direction is parameterized by theta r, and you make theta r increase steadily. So this flow describes anti-clockwise rotations of a radius L. You can check that it is uniform ideal, and hence you build on translations and use the straight kernel that we defined before. And it works in the following way. The rotational motion triggers an event. At the event, you apply the kernel to the instantaneous velocity, and then you infer the new flow variables to go on with the trajectory. Now we can go back to the problem we had with dimers. So the problem was that in the example we saw, we broke the symmetry between the two colliding spheres. To recover the symmetry between the colliding spheres, what we're going to impose is a symmetry between the two spheres inside a dimer. And we're going to impose that the velocity of each of these two spheres is uniformly distributed on S1 at a fixed configuration. If you do this, there is only one possible flow that you can write. So first, because you normalize velocities, the center of rotation can only be located on the bisector of the dimer. So this gives you the parameterization we have to take. So the index of the moving dimer I, L, a real number, which gives you the point on the bisector, and epsilon, which gives you the direction of the rotation. To have the uniform measure on S1 for the velocities, we take I and epsilon uniformly distributed. And for L, since you want this angle delta to be uniformly distributed, you have to take a Cauchy law. And also, I just want to mention that it requires scaling the angular velocity with L, but this is less crucial. And this allows to recover the symmetry between the two colliding spheres. So this is our algorithms for non-reversible rotations. And what happens at the event, so you just have to look at what happens with the colliding spheres. You apply your kernel in terms of the instantaneous velocity, and then you move on with the trajectory. The PDMP framework also allows to describe flow switching. And so we will see in 2 minutes that an interesting algorithm is the one where at each event you switch from a translational flow and a bisector rotational flow. So now I want to finish with some numerical results. So first we look at 64 hard spheres at a packing density which is in the vicinity of the liquid hexatic phase transition. We look at the integrated autocorrelation time of the hexatic order parameter, and we look at it as a function of the refreshment distance. So the picture here, so as for the algorithm, we have translations and rotations, both with the straight and direct kernels. What we see here is that there is no clear gain in introducing rotations. However, the behavior with respect to the refreshment distance is a bit interesting because for example, on the straight rotations, it seems that this algorithm is only slowed by refreshment. So you have a regime here, a stable regime for vanishing refreshment. For hard dimers, so we studied 32 hard dimers at a packing density which is not so high, 0.5. We look at the nematic order parameter. In terms of the algorithm that we look at, we have these ECMC plus metropolis rotations. We have our bisector rotation algorithm and our hybrid algorithm where we switch between translations and bisector rotations. What we see here is that the two non-reversible algorithms have the same behavior. There is a slight gain with respect to the semi-reversible one, but we can't really tell between the two. However, at a slightly higher density, what happens is that the two non-reversible algorithms behave very differently. The bisector rotations perform worse than the semi-reversible algorithm. And this may be due to the fact that as the dimer system is strong, has these really strong correlations because of the nematic order, and because the flow itself is strongly constrained by the dimer geometry, we reach a point where introducing back some translations allows to add a little bit of noise, which seems to be beneficial here with the hybrid algorithm, which is slightly better. So to conclude, so we wanted to introduce general flows in Event-chain Monte Carlo. We provide a method to do that. So with the notion of uniform ideal flows, where independently of the potential, you can construct the setting for your flow. If you conserve probability in V and volume in X, you can just build on translations. This allows us to introduce purely non-reversible flows for the hardcore dimers with a little bit of numerical speedup. And there remains some open questions. So obviously, what happens in terms of large N? So what are the scaling properties of our new algorithms? Also, we did this whole, we designed a new algorithm for hard dimers, but what happens for general particle geometries? And also, these algorithms seem to depend only weakly on refreshments. So could we get rid of that? And if so, could we hope to find a proof of ergodicity with no refreshment? And with that, I thank you for your attention.